Hello, is that okay? Sound? Is that better? Is that okay? All right. Hi, I'm very happy to be here. Thank you for having me. Super excited to see our project out in the world. I'm going to caveat this talk with saying it's been a little while since I had done a talk and I had a baby. And you know that your brain does like all this pruning when you have to go through pregnancy and baby? It's pruned out my entire PhD and most of my linguistic ability. So please bear with me as I might struggle for words, or we'll see how it goes. So I'm here representing the project that I've kind of been a part of, but it's very much been a group effort. So I thought I'd introduce all of us. So me, I'm Jo. I'm a science communicator. My background is in astrophysics, but I really enjoy the places where art and science meet, how we can get science into places that we don't usually see science, and that's kind of a big drive behind this project. But I've been working on it with lots of other people. First and foremost, Max, my partner, said baby. So if she makes a lot of noise, she's an important part of the project too. So, but Max is the photographer, so I'll credit to him for actually taking the pictures. And then I've just... Yeah, it's working. Other kind of collaborators. Elena, she was doing her PhD at the same time as we were. She's the one who got us thinking about the kind of science behind this project, and she's been a real sounding board and helpful person all the way through. And then Graham, finally, our model, not a real astronaut, but a fantastic actor and science communicator as well. So it's been a bit of a group effort. It's been a long time in progress. We started this before COVID, and then everything ground to a halt. So very, very happy. This is its first outing. So really nice to see it in the world and have people engage with it. So I thought I'd start by just talking about the science, which is like the opposite way than I usually talk about it, but bear with me. So this is a picture of the Milky Way, our galaxy, one of the most comprehensive pictures of the Milky Way. And the Milky Way is made up of approximately 100 billion stars. So if we think about just the numbers game, we've got one star, the sun, that has 8 planets in our solar system orbiting it. We've got one Earth that definitely has life, right? And other places that we still don't really know. There are a few places in our solar system, moons and things, that could potentially have some form of life. We've not even explored our own backyard in that respect. We look out further, I think it's just a numbers game. There's so many stars out there. We know that on average, each star has a bit more than one planet orbiting it. That's an average. So there are surely some stellar systems out there in our own galaxy that have some kind of life. It would be crazy if there wasn't. The chances of us ever interacting with it, I think, are fairly slim. But I think it must be out there, or has been, or will be. So we're kind of exploring that idea. So we know that a lot of these stars have planets going around them, and we call planets orbiting distant stars exoplanets. So that's really the focus. Max, his PhD was on exoplanets. The planets we're exploring here are exoplanets, planets orbiting stars other than our sun. We know they're there because we've seen them. The animation is working. So a handful of exoplanets have been viewed directly with telescopes. So this is a GIF of observations of a star with 4 planets orbiting it, at least 4. You can see the 4 bright dots, but it's very difficult to see a planet orbiting a star. Yeah. Stars are incredibly bright, and planets are very faint. So you need to block out the light from the star. You need to kind of force an eclipse on your telescope. You need to block out the light from the main star so that you might be able to capture the faint light of the planets orbiting it. And even then, the planets need to be very, very bright planets, so large planets that are reflecting quite a lot of sunlight, or starlight rather, for you to be able to spot them. So only 98 exoplanets have been detected by this direct imaging method. I think it's the most intuitive. You look out, you see planets. Great. But it's very, very difficult to do that. You need them to be large planets. You need to be able to block out the light from the star. And you need them to be oriented such that their orbits are going around the star and quite distant from their star. And the kind of planets we can detect like this are not ones that you would want to live on. They're large, gassy, very, very hot, not very habitable. the way that the vast majority of exoplanets have been detected, I forgot to say the number, there are 6,600, I think, ish exoplanets that have been detected, and 4,000 of those have been detected via the transit method. So this is a diagram that shows how we do that. It's essentially when we have a kind of eclipse, a transit, when a planet passes in front of the star. So when it's in the part of its orbit that is between us and the star, and it passes in front of it. If we're just looking at the light from that star, we can't see the planet, it's far too far away, it's much too small. We're just looking at the light from the star, we will see a dip in the amount of light. The star will get slightly fainter when the planet passes in front of it. And it will get slightly fainter in a characteristic way, depending on the properties of that planet. So we can tell roughly how big the planet is, its radius, just by how much light is blocked out from the star. So there have been various telescope missions to capture as much information about as many observations of stars as we can to spot when we have these periodic dimmings in the stellar light. So you can see at the bottom this chart of brightness, its light curve, shows that when the planet is passing in front of the star, we see that dip in the light. So that's how the vast majority of exoplanets have been detected. There are a few other ways. There are many other ways. I can't talk about them. Max can talk about them better. So I'm going to defer to him at the end of the talk if anyone's interested. Not all stars are equal. So if we're looking for stars that have planets going around them that might be habitable, that we might be able to have some kind of life growing on, it's good to know a bit about the star to begin with. So these, I've got a kind of the different categories of stars that we see. These are normal middle-aged stars doing their thing, burning hydrogen. But if they're very, very massive, they burn very, very hot, and they are blue giants. And if they are very, very, well, as their mass decreases, they get cooler and cooler in terms of surface temperature, all the way down to tiny M-dwarf stars, which are very cool, very red, very small. Their lifespan also goes inversely with their size. These very massive blue giants burn through all of their fuel very quickly, they're very short-lived stars. In the middle, we've got a G star, like our sun is a G-type star. It has a lifespan of about 9 billion years, and we're about 4 billion years through that now. But M-dwarf stars have lifespans older than the age of the universe. They will burn for billions, hundreds of billions of years potentially, because they burn so slowly and coolly. And they are the most numerous stars in our galaxy. About 76% of the stars, it depends on the estimate you look at, but about 3/4 of the stars in our galaxy are M-dwarf stars. They're very, very common. Yet, if you look up at the night sky, you won't see any of them. They're very faint. You need a telescope to be able to detect these. Because they're so numerous, they're a good place to start looking for planets. And lots of them have planets. They're cool. They have a nice, easy, habitable zone quite close to their star. And they're very common. But life on those stars would look quite different than life on the Earth. So I've got this plot at the bottom. I don't think my head's in the way. But I zoom in a bit here. You can see the spectrum of light that comes from two different types of stars. The yellow one here is the sun, a G-type star. And the red one here is from an M-dwarf. And you can see that spectrum is shifted. It peaks in the redder part of the spectrum, whereas the sun's light peaks in the green of the visible range of light that we see. So if life were to evolve on a planet like that, it would have to evolve to make the most of a very different kind of light than the light we have here on Earth. Another reason that we were interested in M-dwarfs is that our nearest neighbour star is an M-dwarf. So if we look out from the sun and we go to the nearest star systems, we get to Alpha Centauri and Proxima Centauri. Proxima being the closest, it's in the name. And Proxima Centauri is an M-dwarf. You can't see it with the naked eye. Oh wait, actually, let's see if this works. I have a little video. Can I show it? No. I'll show you a map of the sky. So this is the night. It's in the southern hemisphere. So if you can see in the center of this, there's the Southern Cross. And it's in the constellation Centaurus. You can see Alpha Centauri and Beta Centauri are in the knee and the leg of the Centaur. And Alpha Centauri is just tucked away underneath Alpha Centauri. So it's a very small star, an M-dwarf star, very cool, very red. And we know it has a planet orbiting it, which is pretty cool. So if we were going to go to another star system, which is a big if, but if we were going to go, that would probably be the first place to go, because it's only 4 light years away, which is an impossible distance, but it's the closest. So we wanted to explore the idea of what life could look like on our nearest neighboring star system. If life were to evolve on the planet that orbits Proxima Centauri, which it may well be, what would it look like? And because life has evolved there, would have evolved there under a very different spectrum of light, shifted into the red, we can imagine that life would make the most of that. In the way that life on Earth has evolved to make the most of a spectrum that peaks in the green, we have foliage that is green. If we were to have some kind of analog of vegetation on Proxima Centauri b, would it be red? Because that's where the peak of that spectrum is. And that's a big kind of assumption, but it's an assumption that is fairly widespread in astrophysics and exobiology. So we wanted to explore this idea using a film called Kodak Aerochrome. Max, who's disappeared with my baby, she was obviously kicking off. Max was experimenting with this film just with an interest in photography. This was way back, maybe 2018. He bought a roll of 35mm, had a fun shooting it. This is a picture of the department where we were working on our PhDs in Aerochrome. And we showed it to our friend who works on M-dwarfs, and she was like, that's really cool. That kind of looks like what things could look like on a planet orbiting an M-dwarf. So this film is sensitive to the colors that we can see with our eyes, the light we can see with our eyes, but also into the near infrared. And that captures this reflectance from chlorophyll. Chlorophyll that's in all of the green vegetation we see reflects really, really strongly in the infrared. So when you photograph it in the infrared, foliage comes out bright, bright red. And it gives you this kind of strange effect. We've got a picture here in black and white infrared film, which we were also playing with. So you can see that the river in this picture and the trees are dark, but all of the leaves are really, really bright. And there's also a little plot of the reflectance spectrum of chlorophyll there. So it's unusually bright compared to, so if we see it like around the middle, there's like a little bump around 550 nanometers. That would be green, where it's reflecting in the visible light. You can see it shoots up as you go into the longer wavelength infrared radiation. We shot it on this beautiful, it's actually sitting over here, I didn't need a picture of it on a slide. We've got our camera modeling in situ as a lovely Yashica twin lens reflector. By the time we'd got around to deciding to do this project, all of the 35mm film was gone. Kodak Aerochrome was discontinued in 2011, so there wasn't a lot of it left. Someone had cut up all of the remaining stock onto medium format film, so we had to learn to do that. We found ourselves a medium format camera, and we shot these photos in medium format. How long have I been talking for? That's good, because I don't have a lot more to say. So, my hope with this project was to bring some of the questions and creativity and speculation involved in astrophysics, in particular exobiology, I suppose, because we don't know, right? We don't know. One of the things I really love about astrophysics, and I think the reason I got into it, the very first lecture I did as an undergrad, that you can immediately ask questions where the answer is, we have no idea. And you don't need to know much physics or much about the universe to ask these questions. And I think that's a really important thing, that these questions are really accessible. We can all ask them together. We can all explore and imagine together using the little bits of information that we do have. So I've got some more pictures just on the slides. So we've also got these pictures. We've got 4 more up in the bar, in the gallery at the back there. And we've got some of the film positives. So Kodak Aerochrome is a positive film, it's like a slide film. Rather than negatives from the camera, you get a positive. So we've displayed them on a light table so that you can have a look at them. We had to bracket this film a lot, which means we took a photo at the exposure that we thought was correct, and then we took one that was a bit darker, and we took one that was a bit brighter. Because the camera's light meter is not sensitive to infrared. You're not usually interested in the infrared light. So you have to kind of guess how much extra light the camera might be getting that will expose the film. And we guessed wrong quite a lot because it's really hard to know. So you'll see some of our less successful images. For example, we have one of a hillside that was all grass. So it was really, really bright in the infrared, and all of our images are overexposed. So it's it feels like quite a careful project because we only had a few rolls of this film. You can only take 12 shots per roll, and we wanted to take 3 photos for each shot. So that's 4 pictures outcome from each roll. So yeah, Max has been shooting 2 of our additional rolls of Aerochrome around the festival site over the last couple of days. So I hope we can share those somehow after the festival. I don't know. We need to send them off to be developed because it's not a straightforward developing process. And yeah, if anybody has any questions, or if you have anything that you would like to say to us about the project, your thoughts, I mean, I would really love you. We have to do a little report because we did get some funding from the Royal Astronomical Society, and I did set up a voicemail. So if anybody wants to leave us a message, I'd be really happy. It's red 0, so 7330 red 0. If you'd like to leave a voicemail, just to hear people's thoughts would be really lovely. We're also very much open to collaborations and input. I really want to work with other artists and scientists on this to turn it into something a bit more immersive, a bit bigger. Yeah. So thank you so much for having us. It's been really inspiring having conversations here and seeing what other people are doing. So thank you.
Do you have any questions? Red stars are a little bit unstable, aren't they? They flare all the time.
Yes. Yeah. In fact, let me skip forward. Can I skip forward to... Oh, no. This one. Hang on. There we go. Yeah. So, exactly. Red dwarf stars are not as reliable as stars like our sun. So this is a nice... I must say a lot of the graphics in this are taken from NASA and the European Southern Observatory. They have phenomenal educational resources, so I have shared some of those for this. They give off a lot of X-ray radiation and a lot of flaring. It depends on the age of the star. If we can have an estimate of the age of the star, they grow out of that eventually. So, yes, but in reality, there are some good clues that Proxima b, the planet going around Proxima, is not a very habitable planet. So we're running with it, but yeah, it's probably not got life, not at the moment anyway. So this diagram just shows at the bottom we've got a star like our sun. So we've got the X-ray irradiance, the amount of X-ray radiation on the surface is 1 if compared to the Earth's X-ray irradiance, and they have a lifespan of about 10 million years. You can see their relative abundance, so they're not as common as K dwarfs, which are slightly cooler. They have 25 times the X-ray irradiance on their surface, but they're more numerous and they have a much longer lifespan. M dwarfs, much more abundant, but they have 100 times the X-ray irradiance. As I'm sure you're aware, X-rays are not good for bodies, not good for things that want to be alive. So it's not a great start for life. But as I said, depends on the star, depends how long, depends on the atmosphere of the planet, if the planet has an atmosphere. Unfortunately, Proxima b doesn't seem to have an atmosphere that's been detected. And it's also tidally locked to the star. So the moon is a great example of this. The moon is tidally locked to the Earth in that we always see the same face of the moon. As it orbits, it rotates at the same rate that it orbits the Earth. So we always see one side of the moon. The other side of the moon is always away from the Earth. In a similar way, Proxima b is tidally locked to the star. So there's always one face of the planet facing the star, and the other side will be dark, which means you have one very hot side and one very cold side. And then, if there was an atmosphere, terrible hurricanes at the intersection of those points. So, not the loveliest place to live. But yeah. Sorry?
Especially the surface, if there is life properly.
Yeah, right, sure. So yes. But when we say life here, it's with a very big pinch of salt that we're talking about life that looks like life we understand, that has water. Liquid water is a key component there. And yeah, it could be somewhere deeper on the planet, somewhere subsurface, oceans, and all kinds of interesting things. I think one of the things I'd love to explore is looking at the diversity of life forms on Earth, that we actually have some very varied environments and different evolutionary paths and different processes that life operates by, which I think is our closest way to kind of imagining what alien life could be like. Yeah. Any other questions? Yeah, you can take infrared pictures with digital cameras. Digital cameras have an infrared filter on them because the sensor is sensitive to infrared, but you usually don't want that in your pictures. So if you're willing to take apart a digital camera, scratch off an infrared film, and then you want to probably put another filter on top. So if you look at the Yashica over there, you can see there's an orange filter on the bottom on the lens, and that's to cut off some of that blue light to get the effect that we were aiming for in these photos. But people play around with different filters, and so likewise you can play around with different filters on digital cameras as well. Yes, I really like, I think coming from astrophysics, light is the only thing you have to go on in astrophysics, pretty much. Not the only thing. There are a handful of other methods of figuring out what's going on in the universe, but the vast majority of astrophysics is just using light. So I really like the fact that we're using a very tangible process picking up that light. I mean, obviously a digital camera works by picking up light as well, but there's something about the film and the infrared and like the connection with the way we were doing science as well. So.
Also, it's really cool film stock.
Yeah.
And it was very nice to get to shoot it.
Yeah.
It's pretty much gone now. And you can technically do the same thing with digital, as Joe said. But yeah, also you just put a weird filter on top and put it by a camera. It feels like too far to go when the film is there.
And I'm sure I've seen so many people with film cameras around the site. There's a lot of appreciation here for the analog process as well. It's quite satisfying in and of itself. Cool. Oh, do you have another question?
Okay. How did you select the locations for the photos?
We just tried to find the weirdest places we could find within a driving distance of where we lived, which is Edinburgh. Big shocked face. Are you also from Edinburgh?
No,
Yay!
no.
Oh no, sorry, the one behind you. Sorry. Yay, Edinburgh. So these were shot at Aberlady, which is a beach. There's a nature reserve just outside of Edinburgh. And we also shot some at like a big kind of slag heap thing outside of Edinburgh as well.
So some of these are in like industrial ruins.
Yeah, so these ones are the structures that you see here. These ones are coastal defense, like concrete coastal defense stuff. And then this is the wreckage of a submarine from World War II. I quite like that you can't really tell if it's organic or not. It's, yeah, could be an alien whale. Yeah.
Can I talk to you later?
Yeah.
Just like afterwards.
Yeah. I really want to do something with this in Edinburgh, like something bigger. But I don't come from an art background, so the whole exhibition stuff is all very new to me. So yeah. Anyway, sorry.
You have some questions, yeah, I was wondering, do you have a guess as to which kind of form of life that we have in the pictures might be the most likely to be able to survive in a really harsh environment?
That's a good question. I don't know. I'm not an exobiologist. I wish I knew more about it. Right. I was having an interesting conversation with someone about forms that have come up through various different evolutionary paths. Is there a likelihood that, things like everything becomes a crab, right? Does that mean that aliens are going to be more likely to be crab-like? Is that a thing? I don't know. These are good questions. There's surely people here who know more about it than I do, but it's something I want to explore, right? We had to go with the life forms that we had access to, sadly. But yeah. Are we all? Yeah.
Can you join me in thanking Joe?
No, thank you.